Let's talk about Seepage. So the reference book for this discussion is still again the book by Braha M. Das, no, The Principles of Geotechnical Engineering, 7th edition. First, let us define what is seepage. So seepage in soil engineering is the movement of water in soil. So often a critical problem in building foundations. So seepage depends on several factors including permeability of the soil and the pressure gradients. Essentially, the combination of forces acting on water through gravity and other factors. So we have considered some simple cases for which direct applications of Darcy's law was required to calculate the flow of water through soil. So in many instances, the flow of water through soil is not in one direction only, nor it is uniform over the entire area perpendicular to the flow. So in such cases, the groundwater flow is generally calculated by the use of graphs referred to as flow nets. So the concept of the flow net is based on Laplace's equation of continuity, so which governs the steady flow condition for a given point in the soil mass. So now let us talk about Laplace's equation of continuity. So to derive the Laplace differential equation of continuity, let us consider a single row of sheet piles that have been driven into a permeable soil layer shown here. No? The row of the sheet pile, here is the sheet pile, is assumed to be impervious. So meaning water cannot flow through it. So steady state of flow, the steady state flow of water from the upstream to the downstream side, no, through the permeable layer is a two-dimensional flow. So, kung sabi ni Saya pa, ang tubig kuno dire, no, which has a higher elevation compared to the other side of the sheet pile, the water daw will flow from this side to this side through the permeable layer beneath it. So kaning tubig dire, musunob siya dire and then it will travel to the other side of the sheet pile. So in here we are going to identify the rate of flow, no? Or how does the water move through this permeable layer to the other side. So for flow at point A, or here that is yes, here is the point A that we are trying to consider, no? We consider an elemental soil block, no? The block has dimensions dx, dy, and dz. Now, which dz in here, or the dy rather, is the length, no, perpendicular to the plane of the paper. So, more siya pa 3D na siya nga part na, no? So if we are going to enlarge this part here, this point A, it is going to look like this, no? So this is a part, no, of the permeable soil layer. So this is going to be the movement of our water through this block or through this point, no, in the permeable soil layer. So let Vx and Vz be the components of the discharge velocity in the horizontal and vertical directions, respectively. So the rate of flow of water into the elemental block in the horizontal direction is Vx dz dy. So the rate of flow daw sa tubig nga mosulod diri padung nga direction, no, is equal to V dz Vx rather Vx dz dy. So that is basically just the area, no? Because we know that the rate of flow, which is q, is equal to v velocity, no, the discharge velocity times the area, which is dz times dy, no. So vx in here is the rate of flow that will pass the rate of flow of water that will pass through this part here, and then the area which the water will flow into would be equal to dz over dz times dy rather. So, um, and in the vertical direction, it is vz dx dy. So, the rate of flow do nga mosulod diri sa tubig from the bottom up, no? It would be vz, which is the discharge velocity, no? Padung dito, times the area, no, of this one, dx times dy. So the rates of flow from the block in the horizontal and vertical directions are respectively mao ni siya, no. V, this is the discharge velocity, and then the area, no, because Q is equal to VA, and this is V and this is A. So na siya differential diri, no, because with respect to X, no, our discharge velocity along x, or the vx, will move, no, will be, yes, will move because there's a movement of water. So we have to incorporate here the differential expression. So this equation, no, this is an expression now inside the parentheses is the discharge velocity, and the dz and dy are the dimensions which the product of which will result to the area, no, so as well as along the vertical direction. So assuming that water is incompressible and that no volume change in the soil mass occurs, we know that the total rate of inflow should be equal to the total rate of outflow. So thus, muna siyang equation, no? The sum of the inflow should be equal to the sum of the outflow. So simplifying this equation, we would come up with this equation only, no? So this is Laplace equation of continuity. So with this one, no, and then in combination with Darcy's law, which says the discharge velocities can be expressed with this one, no, Vx is equal to Kxix. Therefore, we can write this equation to this equation, no. So if the soil is isotropic with respect to the hydraulic conductivity, that is Kx, Kz, no, or they are both equal, no, to each other, this equation or this continuity equation for two-dimensional flow could be simplified to this one. So man ni siya ang final, no, nga equation of continuity by Laplace. So this equation can be used to solve, no, simple flow problems or simple um, situations, no, that would require us to compute for the rate of flow. So another thing about seepage is the flow nets, no. This is very much common when you talk about seepage. It would directly mean the flow nets, no, because we would calculate the seepage through the flow nets man. So the continuity equation in an isotropic medium represents two orthogonal families of curves, that is the flow lines and the equipotential lines. So kaning si flow lines o si equipotential lines mo ni sila ang ga-make up sa atong flow nets. So a combination of a number of flow lines and equipotential lines is called a flow net. So as mentioned in the introduction, flow nets are constructed for the calculation of groundwater flow and the evaluation of heads in the media. So therefore, flow nets will enable us to calculate the groundwater flow and as well as the heads, no, and it enables us to evaluate the pressure heads, no, inside our permeable soil layer. So let us first define what is a flow line. A flow line is a line along which a water particle will travel from upstream to the downstream side in the permeable soil medium. So basically, muna siya atong flow line, no, that is a line, no, which our water will travel from the upstream to the downstream. So ani siya ang flow line, no. Ana ang itsura sa flow line. It is a connection, somehow a connection, between the upstream and the downstream side of our permeable soil layer. Now, the equipotential line is a line along which the potential head at all points is equal. So that's if piezometers are placed at different points along an equipotential line, the water level will rise to the same elevation in all of them. So ang equipotential line, muna sila, no? So along the equipotential line, kung magtusok daw kadara og piezometer, no, in doesn't matter, no, kung unsa nga depth, no, along the equipotential line, equal na gyapon ang yahang water level diri sa piezometer nato, no. We have here first one, no, kaning piezometer on the right. So it was inserted to adapt in here, and it has attached the equipotential line, because equipotential line will look like this one, man. So it will intersect. It is somehow an inverted flow line, no? So it will intersect the equipotential line at this point, and then the water will rise at these levels. If you are going to insert another piezometer, and then it will hit or to a certain depth, no, in the equipotential line, which is this one. So the rise of the water in this piezometer will just be equal to the rise of the water in this piezometer. So ano yung pasabot? So muna siyang equipotential line, no? So if you're going to combine the flow line and the equipotential line, it will um look like this one. So flow nets, no, actually flow nets should be constructed, no, more than one. So it is actually upon the problem or the discretion of the ones solving, no, kung pila ka flow line iyang i-construct. But most of the time this is given, no, in most problems. So if you're going to combine the flow nets, no, and the equipotential line, so this is what we call the flow net, no, flow net. So we have here the number of flow lines designated by n sub f, which is the number of flow line lang, ihapo lang nimo siya. 1, 2, 3, 4. So actually, gi-appeal niya, no? Yes, it is 1, 2, 3, 4, no? Ang NF diri is number of flow channel, meaning kani bitang divisions, no, that was made from our flow line, no. This is NF is 1, 2, 3, and 4. And our number of drops would be equal to, so let us write that down, no. So our number of flow channel or n sub f is equal to 4. So we have 1, 2, 3, and 4. So for our ND or number of potential drop, although I will be explaining this further, but at least by this part of the discussion, you would already know the what or how to count the number of drops, no. So ang number of drops is ang number of pila ka squares, no, number of squares nga or approximately squares nga na-create, no, with the intersection of our flow nets and the equipotential line. So for this one, we are going to count, no, we have 1 square. So pwede ra ka mamili, no, which flow line you are going to refer to. So it would be easier for us to refer to an inner flow channel, no, kaning murag tunnel ba tawag ani, murag tunnel siya, no, or a flow channel. This is what we call the flow channel. So mag-refer to dito nga, no. So if you are going to count the number of drops, you have, that is the number of square, no, approximate square. So we have here 1, 2, 3, 4, 5, and then 6. So, pareha ra gyud na siya, no, kada flow channel or kada NF, yes, kada flow channel, same ra na siya na number of squares, which is the number of drops or number of equipotential drops. So, if you're going to refer to this outer flow channel, no, mag-ihap ta diri for the number of drops. You have 1, 2, 3, 4, 5, and then 6, no? So, muna siyang atong ND, diha nga part. So, and then the H in here is the water level, no, in or on point B, which is the upstream, and then H2 is the water level on the downstream. So a combination of a number of flow lines and equipotential lines is called the flow net. So as mentioned in the previously, no, flow nets are constructed for the calculation of groundwater flow and the evaluation of heads in the media. So to complete the graphic construction of a flow net, one must draw the flow and equipotential lines in such a way that the equipotential lines intersect the flow lines at right angles. Number two, the flow elements formed are approximate squares. So in this figure, we have here this two, no? NF is the number of flow channels in the flow net, and ND is the number of potential drop. So we have here in the example, no? Iyahang giingon daw dire. We have, let us consider first this one, no? The upper figure. So let us count the number of flow channels or the NF. So that is 1. Let us have that color red. We have 1, 2, 3, and 4, no? So that is 1 flow channel, 2 flow channels, 3 flow channels, and then kaning gamay din, no? Fourth or 4 flow channels. Now let us count the number of drops or the ND, no, for this flow net here. So we are going to refer to the inner flow channel. So we're going to count now 1 number of drop, 2, 3, 4, 5, and then 6 number of drops. So if we are going to confirm that one, no, we would consider this outer flow channel. So we're going to count number of drops. 1, 2, 3, 4, 5, 6. So the number of drops is just equal, no, kada flow channel. So if we are going to consider this, no, here, this figure here, we are going to count the number of flow channels or NF and the number of potential drop, which is ND. So let us first count the number of flow channels. So in this case, no, na-drawing na kibali, no, ang atong flow net. So wherein na-draw na nato ang atong flow line and the equipotential lines. So in some cases, we might be needing to draw or construct our flow lines and equipotential lines. And there are also cases nga gibuhat na sila, no. So all we have to do is count the NF and the ND and then perform the calculation needed. So if you're going to count, no, the number of flows for this one, we have 1, 2, 3, 4, and then kani gamay diri, no, kani siya 5, no. So basically 1, 2, 3, 4, 5 number of flow channels. Okay. So now for our number of drops, we are going to consider the inner, no, flow line. So for example, we are going to count here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 daw ka number of potential drops or 9 daw ka approximate squares ang naa sa isa ka flow channel. So man yang pasabot, no. So if we're going to verify that one, let us consider this outer flow channel, no. So let us count the number of squares or that is equal to the number of potential drops. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9. So equal lagi siya na number of drops is just equal to the number of drops with other flow channels. So nganong man, no, nga kailangan nato ni ihapon ang number of flow channels, a number of potential drops rather, or the NF and the ND, because later on in the calculation of the seepage, no, we will be needing this value no, kay naa sila sa mga formula nga atong panggamiton. So that's why it is very much important for us to know how to count, no, or how to identify the number of flow channels and the number of potential drops. So drawing a flow net takes several trials. While constructing the flow net, keep the boundary conditions in mind. For the flow net shown in this figure, the following four boundary conditions apply. So if you're going to make or to construct your own flow net, then these are the conditions that you have to follow. So the upstream and downstream surfaces of the permeable layer are equipotential lines. So meaning apilon daw ni siya no kaning AB, this one, AB and DE are actually equipotential lines. Ang mga equipotential lines no. So meaning atong equipotential lines diri is we have 1, 2, 3 and then apil nung ihap no ang kaning AB and then DE. Apil daw sila sa equipotential line. Pero di na siya maka-affect no dito sa atong pag-identify sa atong NF og ND. And then the second condition is because AB and DE are equipotential lines, all the flow lines intersect them at right angle. So meaning mo itong flow line no. So kada intersect daw sa flow line diri nga point, it makes a 90-degree angle as well as this one, this point, this point, this point, this point as well. So condition number 3, the boundary of the impervious layer, that is line FG, this one, is a flow line, and so is the surface of the impervious sheet pile line ACD. So apil na siya sa ihap no sa atong flow line na kining ACD, and then apil pod ni siya ang kating FG. Apil doon na siya sa itong flow line. So, you have this flow line, no? Flow line, and flow line. So, therefore, in this figure, we have 1, 2, 3, 4, 5 flow lines. So, we should not be confused between the flow lines and the flow channel, no? And the number of drops, or the number of potential drops, and the number of equipotential lines. So, lahi na sila, no? And the condition number 4 is saying that the equipotential lines intersect line ACD and FG at right angles. So kani ko nung equipotential lines diri no? Kani dong equipotential line makes a right angle with the line FG daw. So kani ko diri makes a 90-degree angle and as well as this one. So ano lang. Okay, now so let us talk about how do we calculate seepage from our flow net. So in any flow net, the strip between two adjacent flow lines, no, is called a flow channel. So mo to ganyan no. Flow channel na siya. So if you are going to magnify sa katong mga lines sa ganiha, muna siya, this is how our flow channel looks like, no. We have here kani, this one is the flow line, and this one is our let's put that green, is our equipotential lines, no? So kada intersection nila duha, no? So this is the equipotential line kani siya diri nga part, and then this is the flow line, no? Oh, sorry. Let's make that a yellow. 'Di ba? Sa katong number of equipotential drops, number of squares mo totong ihapon. So mo ni siya no, ang ma-create sa intersection between the flow lines and the equipotential line. So figure here shows a flow channel with the equipotential lines forming square elements. So let H1, H2, H3 no be the piezometric levels corresponding to the equipotential lines. Okay, the rate of seepage through the flow channel per unit length, no, to the vertical section through the permeable layer can be calculated as follows. Because there is no flow across the flow lines, the flow in this square 1 is just equal to the flow in square 2, and as well as the square as well as the flow in our square T. That is Q1 is equal to Q2 is equal to Q3 and is equal to the other flow or rate of flow sa kada flow channel or sa kada square, no? So from Darcy's law, the flow rate is equal to, di ba, Q is equal to VA and V is equal to KI. So therefore, Q is equal to KIA. So thus, this can be written as K is equal the flow rate, the flow rate is equal to K I and then A, no? So we might have wondered nga nung inani may itsura, no? This is the K, obviously. This is the I, kaya nasa sulod sa parenthesis, no? Because we know I is just the slope or the rise over run. So meaning the rise would be h1 minus h2, the difference between the piezometric level, no? So for example, we're going to consider uh, this square right here. So we're going to consider that. So iyang hydraulic gradient daw diri is just the slope, no, of the water, meaning rise over run, that is h1 minus h2 times the length of flow L1. And this L1 in here is actually the area of which our water will flow into this part. No nga nung di siya L times L, no? Kay L man daw ang diri L man daw ni siya nga dimension and then L po na. So actually dili ni siya mao nga area, no? We are going to consider the area perpendicular to this one, no? That is L1 man ni siya, no? L1 and then 1 meter strip perpendicular to this surface here. So that is length 1 or L sub 1 times 1 meter. So that's why the area in here is just L1. Well, actually, nana siya 1 diri, no? Which represents the 1 meter strip consideration. Pero, which is perpendicular to this one. Wala na siya gibutang ang 1 kay negligible mangyapon siya, no? So the flow rate for this square is equal to this square is equal to this square. So muna siya nga formula, no? We just substituted or transformed this formula in here to this one. So it shows that if the flow elements are drawn in approximate squares, the drop in the piezometric level between any two adjacent equipotential lines is just the same. So this is called the potential drop. So kaning H1 minus H2 is just equal daw to the rest of the approximate squares. That's why we can simplify that with the total H is divided to the number of drops. Ka-equal naman din sila, no, sa kada isa nila. So therefore, our flow rate now becomes this one, K times H over ND, where H is the head difference between the upstream and the downstream sides, and ND is the number of potential drops, the number of squares or approximate squares in a flow channel. So muna siya ang equation na dayon nga atong gamiton for the calculation of seepage from a flow net. So if the number of flow channels in a flow net is equal to NF, the total rate of flow through all the channels per unit length, no, per unit length, something 1 meter strip of an isotropic soil can be given by K H times NF over ND. So actually, kato ganihan, no, katong delta H is equal to K times H over ND is actually the rate of flows kada isa ani nga square. So kung mingon kag total flow, no, you just have to multiply that one with the number of flow channels, no? Kibala mo siyang Q is equal to K times H over ND times NF, no? So dito malibog, no, kani siya is the total. Ang katong isa ka ganiha in the previous slide is the individual, no, rate of flow sa kada flow channel. So although, no, drawing square elements for a flow net is convenient, it is not always necessary. So nganong gi-assume nato no nga square. Actually gi-assume raman to siya nga square, pero there are also instances nga siguro in some problems i-specify niya dito, no, that our flow channel has a rectangular element. So alternatively, one can draw a rectangular mesh for a flow channel, as shown in this figure, no? So, rectangle siya. Iyahang length is not equal to its width. So, na siya B1 and then L1. Kay ganiha, kay square man totong element, we have L1 ni siya and then L1 pod ni. So, kani diri kay rectangular man daw, so na siya B1 and then L1 nga dimensions. So, but, no, when you actually draw a rectangular elements for your flow channel, you have to make sure that the width to length ratios for all the rectangular elements in the flow are just the same. So, in this case, the rate of flow through the channel can be modified to this one. So, ang nadugang diri is ang kanila yung n, no? Which is the width to length ratio of the elements. Pareha naman siya kh, diba? K times h over nd times nf man to ganiha to sa square elements. So, for the rectangular elements, you just have to add the n, no? Which is the width to length ratio of the rectangular elements. So, we have here a sample problem, no? A flow net for flow around a single row of sheet piles in a permeable soil layer is shown in this figure. So given that kx is equal to kz is equal to the rest of the k, which is equal to 5 times 10 to the negative 3 centimeters per second, we are asked to solve for how high the water will rise if the piezometers are placed at points A and B. No, we have points A and then B. So yung pasabot diri is actually kung mag-insert ka na kog piezometer diri nga point, pila kunoy rise sa water level inside our piezometer, or that is actually the water level no at this point. And then we are asked to solve for the total rate of seepage through the permeable layer unit per unit length and the approximate average hydraulic gradient at point C. Anong point C diri? So for the solution, no, from the figure, we have the number of drops is equal to 6. So we have to count na 1, 2, 3, 4, 5, and then 6. And then our H1 is 5.6 and our H2 is 2.2. So, the theory behind this is ang movement kuno sa atong water from the upstream to the downstream, mag-move kuno atong water from this area to this area. And then, as the water flows through this permeable layer, naay mga pressure drop, no? Muna siyang gitawag nga potential drop. So, kung maagi siya diri, ma-reduce ang iyahang water level, maagi siya diri nga part, ma-reduce ang water level diri. So, kada square ani na ay potential drop, meaning the height of the water level in the piezometer once inserted will decrease, no? Will decrease throughout the flow of the water. So, meaning, kung maagi siya diri ang tubig, na siya potential drop ng isa, kung na diri ang tubig, madidaka na po siya og isa ka potential drop, kung dili na po, madidaka na po, so on and so forth. So, at point A, we have to calculate the change in, or the head loss of each potential drop, no? Kada potential drop, na the head loss nga ma-experience atong water as it flows from the upstream to the downstream. So, i-calculate nato ang head loss sa kada potential drop, equal naman na sa each other, no? That would be equal to H1 minus H2 over the number of drops, no? It's actually this one minus this one times divided by the number of equipotential drop, or the potential drops rather, or our ND. So H1 5.6 minus 2.2 divided by ND nga 6 kabuok, no, is equal to 0.567 meters. So kada isa daw ani, kada isa nga square mag-cause, or kung maagi atong tubig dirha, naa siya head loss equal to 0.567. So at point A, no, we have gone through one potential drop. So the water in the piezometer will rise to an elevation of 5.6, no, meaning ang atong tubig will flow man from the upstream to the downstream, meaning kung dili pa siya, ang iyahang pressure head is equal to 5.6, no, minus dayon kinaagi man siya isa ka square, so na siya head loss nga equal to isa ka 0.567, no, muna siya diri. that is equal to 5.033 meters above the ground surface. So whereas our point B, no, if our water were flow from this point to this point, so 5.6 diri minus isa, duha, tulo, upat, lima. Lima ka potential drop yung agian. Meaning, lima pod ka 0.567 head loss ang iyang ma-experience. So, that's why, sa point B, ang the water in the piezometer will rise to an elevation of 5.6 minus 5 ka head loss, no? Kay 5 man ka potential drop yung agian, and that would be equal to 2.765 meters above the ground surface. So, anaon lang siya pagkuha, no? So, the next one, we are asked to solve for the seepage flow. So, we have this formula, no? K is equal to H times NF over ND, no? So, ang kani siya, actually, same naman ni siya, no? Kaning equation is what Braha M das is using, pero similar na siya ng equation, no? This equation is the one most commonly used in review books, and then this one is from Braha das na book yun. So, we have here 2.38, no, which is the constant value, times K, which is given, and then H1 minus H2, 5.6 minus 2.2, over the number of drops, which is equal to 6. So, calculating that one, our seepage flow is equal to 6.74 times 10 to the negative 5 cubic meter per second per meter. So, muna siya ang unit, no, sa atong seepage flow. So, for the last one, we are asked to solve for the average hydraulic gradient at C can be given as, no, we know average hydraulic gradient is just the rise over run, no, that is the slope. So we have to know the H and the L. So the head loss at point C, diri pila head loss diri which is we have previously computed to be 0.567, and divide that one by the length of flow, which is given po, no, 4.1. So dividing this one, we would arrive with our hydraulic gradient equal to 0.138. So ana lang siya na. Ang katuganihan nga consideration is about isotropic soil. So we also have what we call the anisotropic soil, no? So the flow net construction described thus far and derived equations discussed for seepage calculations have been based on the assumption that the soil is isotropic. Meaning, for the isotropic type of soil, meaning yung properties are identical, no, in all directions. So, what if our soil that is anisotropic, meaning our soil has a properties, no, of a material dependent on the direction, meaning dili siya identical in all directions. So, in nature, no, most soils exhibit some degree of anisotropy. So, to account for soil anisotropy, with respect to the hydraulic conductivity, we must modify the flow net construction. So the rate of seepage per unit length can be calculated with this value. No? Ang nalahi diri is ang kaning kx o kz, no? Kay since anisotropic man siya, meaning dili pariha, no, yung characteristic in all directions. So we have to consider different coefficient of permeability. So automatically we just have to use this formula, no, in the calculation of our rate of seepage when the problem specifies that our soil is anisotropic. So note that when flow nets are drawn in transformed sections, or the anisotropic soils, the flow lines and the equipotential lines are orthogonal. So however, when they are withdrawn in a true section, these lines are not at right angles to each other. So this fact is shown in the figure. So, mo ni siya daw. Dili daw siya right angle gidaw. So, in this figure, it is assumed that Kx is equal to Kz. So, figure A shows a flow element in a transformed section, and the flow element has been withdrawn in a true section in B. So, ana daw siya. So, now let us talk about the uplift pressure under hydraulic structures. So, flow nets can be used to determine the uplift pressure at the base of a hydraulic structure. So one example of a hydraulic structure is a dam, no? So this general concept can be demonstrated by a simple figure here, no? It shows a weir, and the base of which is 2 meters below the ground surface. So indicate siya din nakalubong daw siya og 2 meters. So the necessary flow net has also been drawn, no? Drawingan na yung flow net, no? Which composed of um, the flow lines and the equipotential line. So the pressure distribution diagram at the base of the weir can be obtained from the equipotential lines. So you have equipotential line A, equipotential line B, equipotential line C, D, E, and F. So there are 7 number of equipotential drops, now which is the number of squares. So let us count. We have 1, 2, 3, 4, 5, 6, and 7. So sakto no, 7 daw ang atong ND. And the difference in the water levels between the upstream and the downstream is 7 daw. Gihatag na siya diri, oh, this one. The head loss of for each potential drop is, you just have to divide man this, no, the total head difference divided by the number of equipotential drops. So 7 divided by 7 meters divided by 7 number of equipotential drops, we would have 1 meter head loss for each of these equipotential drops. So the uplift pressure at A, no, which is the left corner base, we have here, diri ang A. Diri ang A nga part. So this is A here. So that would be equal to the pressure head at A times the unit weight of water, no? Pressure man siya, so it has to have the unit for pressure, that is force over area. So pressure head at A is equal to 7 plus 2, no? Kay 7 man daw ang tubig, and then nakalubong siya 2. And then sa A is makaagitag isa ka equipotential drop, which is isa ka square, no? So from this one, we have the elevation of the water elevation is 9 minus isa ka equipotential drop. Kaya kaagi mo siya isa ka square diri, ano? Siya diri. Kani nga square. This one. So meaning, from the pressure head here, the water will flow downwards. And then the head here is 9, no? Okay, 7 plus 2 minus isa ka equipotential drop, which is equal to 1. So 7 plus 2, 9 minus 1, that is 8. Times the gamma water. So mani siya din, no? The pressure daw diri at point A, that is the left corner of the base, is equal to 8 times the gamma water. So ana lang siya. So if we are going to graph, no, the rest of the points here, A, B, C, D, and F, so it is going to look like this. So as we have observed, no, mag-decrease ang iyahang pressure head, no, sa kada point as our water flow from this side of the upstream to the other side, no, which is the downstream. Kay kada maagian niya nga square na may head loss. So kung mas daghan nga square yung maagian, mas mag-anam og kadaghan ang ma-minus nga head loss. So paabot niya diri gamay na lang, no, which is now equal to at point F 3 gamma water na lang. So muna siya yung rationale behind. So similarly, the uplift pressure at B, no, and then F, mas lagi represent siya ani nga graph. Now sa B, for example, we have point B, that is 9 minus pila man ka square yung maagyan, let us count, no? 1 and then 2. So 2 daw ka head loss kay 2 man ka square, and then kada square na head loss nga 1 meter. So meaning 9 minus duha ka 1, that is equal to 7 times gamma water. Muna siyang sa point B. That is the pressure at point B. That is also equal to this one here. So at point F, which is this one, no? So let us count, no, the number of equipotential drop that our water will have to pass through. We have ato lang i-yellow, no? So we have 1, 2, 3, 4, 5, and then 6, no? So meaning from the pressure head here that is equal to 9, maminusan siya 1, 2, 3, 4, 5, 6 ka 1 meter nga head loss, no? So that would only be equal to 3 times the gamma water kay pressure man siya, no? So that is pressure due to water, so we have to use the unit weight of water. So meters man, 3 meters times kilonewton per cubic meter nga unit sa atong gamma water, then our unit would become kilonewton per square meter, or that is the force over the area. So man ni siya atong pressure at point F. So we also have what we call seepage through an earth dam on an impervious base. So figure here shows a homogeneous earth dam resting on an impervious base. So let the hydraulic conductivity of the compacted material of which the earth dam is made be equal to K. No? So the free surface of the water passing through the dam is given A, B, C, D. So the water will flow there from A, you have A to B to C, and then to point D, no? Sa anak ko, no? Ang tubig daw gikan diri kay this is an earth dam, meaning it is made of an permeable or a permeable material, no, aside from concrete. So that's why water will flow through it, no, from this point here to this point. So the rate of seepage can be calculated through this equation, no, where L is equal to D cosine alpha, no? Alpha is here, and then the angle beta here. So automatically, if our problem is concerning about the earth dam, and we are asked to calculate for the seepage, and then we are going to use this formula, and this as well. Or we could also use, no, other review books are using this formula, no, for the seepage through an earth dam on an impervious base. So we can use this formula. So same lang gyapon to siya. Katulang kaganiha is more complicated lang to, no, ang gi-present ni Mr. Brahadas sa iyahang equation, no, for the seepage. So pwede ra, no. So kung inaano yung itsura, no, na phreatic line, inanian pag-solve. And then kung inaani pa yung itsura, then inanian po siya pag-solve. So that is just formula based, no. L is the length, no, of the base of the dam. And then H1 and H2. So diri wala siya gihatagan og value siyang L, no. Kay sa iyang formula sa di siya makilangan og L. So H lang ang kailangan, and then number of flow channel kinaman siya mga inaani diri. Gidrawingan siya, no. So ana lang siya. So that would be all about seepage. Thank you so much.